In a typical robot design process, a designer who starts with a goal will first create a general geometry and then specify the movement for that robot. In this linear process, both motion and geometry design are optimized for separately. However, fixing a geometry at a first stage constrains the motion design and may force suboptimal performance. For example, let's look at this robot that a user designed to deliver ice cream. The fastest motion for this topology comes from moving all the legs in parallel. However, using that motion on this design causes the robot to topple over and all the ice cream will spill out. We can change the motion to have the legs on the right move first, allowing the robot to move forward without toppling. But even further, widening the back of the robot makes it stable with respect to the optimal gait, almost doubling the speed compared to the original geometry and drastically reducing the amount of wobbling. We propose a design tool for ground robots that enables users to explore the combined geometry and motion design space. Our tool tightens the feedback loop between the two stages of the design process, making it more efficient and intuitive. Using our tool, users create a geometry by selecting components from a part library, manipulating the shape parameters, and composing parts together. We have classified parts into bodies, wheels, legs, and peripherals, and have defined a grammar for composition. Similarly, the users design a gait for the robot by selecting gaits from a list of suggestions and modifying the gait parameters. Different gaits provide different trajectories for the robot and can be previewed. In this example, the blue gate makes the robot move forward, and the orange gate makes the robot turn. The design gates can be composed together into a gate sequence. The system computes relevant metrics in the design, such as the fabrication cost, speed, and trajectory for each gate and the gate sequence. These are updated in real time as users modify the gate or geometry, allowing them to visualize the effect of both design aspects on the robot performance. Users who want to optimize for specific metrics can ask the system for suggestions on how to edit the robot geometry. Arrows in the UI indicate directions of change that will improve the metric. Alternatively, users can select an automatic optimization method that will search for metric improvements in the full geometry space. For fabrication, the system outputs a plan that includes a mesh to send to the 3D printer, a list of electronics and port connections, and software to load into the microcontroller. Once the user assembles the parts, the resulting robot matches the specification. To evaluate the usability of our system, we introduced our tool to 8 users. The users creatively explored the geometry design tool to produce a variety of wheeled vehicles. An enthusiastic user designed an additional gallery of 18 models using our tool. They also managed to use the gate design tool and interactive feedback to successfully navigate an obstacle course, taking an ice cream truck to a cake while avoiding fruits and vegetables. The users who were allowed to simultaneously edit geometry and gate designed trajectories that were 40% faster on average than the ones created by users restricted to gate design. We have fabricated 5 additional robots with different geometries and gates. Each of them took about 10 minutes to design, 3 to 7 hours to fabricate, and an hour to assemble. The robots all followed the designed gates and walked as predicted by the system.
Robot topology, optimized robot body, a feasible motion trajectory for solving tasks in which foothold patterns need not be specified specifically. We fabricated one of our optimized dynamic robots in order to demonstrate that it could be physically. Our quadcopter has 2 parameters, radius and mass, and must follow a 16 waypoint trajectory, minimizing its maximum power consumption. Our biped has 8 parameters, its base extents, leg length extents, and link masses. It must walk forward, or walk up a step, minimizing its maximum power consumption. Our quadruped has the same 8 parameters as the biped, with a different topology. In the first task, it must walk, minimizing its maximum power consumption. In the second task, it must reach its goal as quickly as possible.
This tailed quadruped has 10 parameters, corresponding to its link lengths and the link masses. It must walk forward a fixed distance, reaching a fixed target height with its body, while swinging its tail up to 1 meter above its center of mass. Each tail link may only flex up to 60 degrees. In this solution, the algorithm discovers the legs must grow, the first tail link and the body length must shrink, and the final tail link must grow.